In this section, we'll be looking at the fundamental theorem of calculus, which we'll use to calculate integrals. We'll also be able to construct a function with a given derivative and value, even if we don't know the antiderivative. So first of all, using the fundamental theorem of calculus, we are talking about a function. If it is continuous on a given interval, then we know that the integral with that function f, if we take the derivative of that function, so derivative of the integral, will give us the same function back. Notice there is a little bit of a change in variables here, where in our integral our lower limit is a constant and our upper limit is the variable that we want in our final function. So again, the upper limit has to be the variable that we're going to plug in, and it also agrees with what we're taking the derivative of. What's important here is that every continuous function, if we have a continuous function, we know that it must be the derivative of another function, which means it has an antiderivative. So every continuous function has an antiderivative. It also tells us that integration and differentiation are inverses of one another. We're going back and forth between those two things. So if I have this problem here, we're asked to take the derivative of this integral. Notice that our upper limit is a variable, x, which agrees here, and the lower one is a constant. All we have to do is say that this is the sine of x. Okay? So think about what we're doing. If we've got this integral right here, and we're asked to find the derivative of it, well, let's look at what the antiderivative of that. The antiderivative of sine would be negative cosine of x plus some constant. If I take the derivative of that, the derivative of negative cosine would be positive sine. The derivative of the constant is 0, so it just brings me back again to what was inside. In this example, we want to find the derivative dy dx, but notice this doesn't fit our formula y equals because this x is x squared and we need to have that variable by itself in order for this to work. What we'll be looking at, since we have y equals this over here, is that we're looking for the derivative with respect to x here for our integral. Now what I'm going to do here, since I can't have x squared, I'm going to change this to just u. I'm going to do a substitution here where I'm going to let u equal x squared. This way I just have a variable up there. The rest is going to stay the same. Okay, now the next problem is that these variables here disagree, and they need to agree in order for this to work, and we're going to apply the chain rule that if we want dy dx, but we're using du, we can do that as long as we multiply du times dx. So I need to take this derivative, since I have u, I need the variables to agree. That's going to be d du, and I have to keep the inside the same. Now I've changed this, so the way that I can keep this equal to d dx is by multiplying my result by du dx. So just like it worked with our chain rule here, that this will leave me with dy dx, which is what we're looking for. So to work this one out, our next step here is just looking at this part right here. Taking derivative, my variables agree, so I can change that to sine of u. But then I have to multiply it by the derivative of u with respect to x. First, let's look back at what that du dx would be. Notice this right here, so our derivative would have to be 2x based on that. We also don't want u in our answer. We wanted this everything with respect to x, so I'm going to plug the x back in. U was equal to x squared. And so my derivative here, I can move the 2x out front, sine of x squared. In this next example, the problem is that the variable is in the wrong place. We want it to be on top. But as we learned our rules for working with derivatives, this is okay. All we have to do is switch the order of our variable. We can do that by making this negative. So now I'm going from 5 to x. I've switched the sign here. And so I can find this derivative. I can move this negative. It's just a constant multiple. I can move it out front. And so I just plug in the x for t to finish the problem. In this next example, we're asked to construct a function, f of x, that has a certain derivative. Now we might think we could just take the antiderivative of tangent of x to find this, but we don't know the antiderivative of tangent of x. We also want it to satisfy the condition f of 3 is equal to 5. So we were given an x value, we want y to be equal to 5. The key to this is with the x value. When we set up our integral, we should remember that if I'm going from one value to the same value, that integral will be equal to 0. And with the fundamental theorem of calculus, we're putting a variable up here, x, because we want a function that has a variable. We want this to be a function in terms of x, and that's where that variable goes. And that's also why we need to have a t, a different function down here, because the variable is up here. So the key has to do with this 3 here. If I put the 3 here, right here, then that tells me if I plug in x, this part of my function will be equal to 0. And if I want this function, y, or f of x, to be equal to 5 when x is 3, if I plug in x right now, I get 0, so I'm going to add something else here. 0 plus 5 would give me 5, so I'm going to add the y value that we want at this point. So I force this integral to give me a 0, and I add on what I want. If we think about this in terms of using area, I've got a function, and I don't really know, this was going to start me at 5, and then when I move on to any other value of x, we're adding to 5, or if we're going backwards, we're taking away from this value of 5, because that's our y value at that point. So the key here, plug in the x value you have down here to your lower limit, plug in the derivative that you want as your integrand, and then the constant value, the y value that you want at that y, that's what you're going to plug in kind of as a constant being added on at the end. In this next example, we want a function, f of x, that has the derivative of sine inverse of 1. So we'll start, that's going to be our integrand, but just remember that we change our variable to t on the inside because our variable is going to go up here, the x. Next, we want to satisfy the condition that if x is 5, y will be negative 3. So we're going to start by putting the x down here. That way, if we plug in x equals 5, it'll go from 5 to 5, making the first part 0. And then if we want y to be equal to negative 3 at that point, 0 plus a negative 3 will give us the function that we want. Okay, what does this do for us? We're given this function here, but that's supposed to be our derivative, so we're trying to go back and look at what our function originally was. We know that we're starting at the point where x is 5, y is negative 3. What this integral will do is, as we move left and right, it's going to tell us what to do, whether we're going up or down from that point. And by accumulating area, we're going to see what this graph is doing. It would also work if we plug in negative values. It would also go backwards and tell us where that graph needs to go. We don't actually need to use the graph, though. This function will allow us to find specific values.